situation with parametric equations can be illustrated graphically in this manner. If we have x as a function of t, then there's some curve that describes x as a function of t. If y is a function of t, then there's some curve, probably a different one, that describes y as a function of t. And we can graphically construct a graph of y versus x just using the graphs of x and y. And we don't really need to do that with a lot of precision. If we know how the function x of t behaves and how the function y of t behaves, then we can get a very good idea how the function y versus x, or the relation y versus x, because it's not always a function, will behave. Okay, so what we do is, first of all, we see that, what we have here isn't going to apply for t values less than right here. So our first t value would be here, and of course we can mark the same t value. I'm assuming implicitly that the t-axis is the same in both cases. Okay, and of course this first value of t gives us a value of x, and of course that value is right here. And maybe I'd better use a distinct piece of chalk. So here's the x value, same value of t gives us a y value. Okay, so when x is equal to this, which is 0, y is equal to this. We can plot that as a point on the axis. X is 0, y is this. Using the same x and y scale that we have on these graphs to construct this graph, we get a point here. Okay, now to get a grasp on the behavior of the function, it helps to just then choose a series of equally spaced t values. So I'm going to space t maybe like so, and I'm going to use the same t values down here. I'm assuming I'm constructing these equally. I can't really see what's directly above or below anything, but you certainly should get the idea. Now the x values, of course, be obtained by projecting directly up to the graph from each of the t values, and then projecting over to the x axis here. So we see that our x values for this function are going to become more and more closely spaced. So we have an x value at 0, we have x value here, 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 and here. I mark those same positions, or positions that are supposed to represent these same positions. In other words, it's going to bring the x-axis down here, and I have marks here corresponding to the marks that I have up here. And I know that these marks correspond to increasing values of x. Now what about my y values? Well, you know, this is a straight line. Okay? If my t values are equally spaced, then my y values are going to have to be equally spaced, because of course the difference in two y values is equal to the rise of the graph, and the difference between the two t values is the run of this graph. If the run is always the same, the rise is always going to be the same. So I don't really need to construct all these to see that my y values are going to be equally spaced, but just to be sure we do every step, there are my y values that correspond to these x values. Now we've already plotted the first point corresponding to this, and now we just have a series of equally spaced y values. Okay, well, this y value corresponds to this x value because it came from the same t value. The values of y and x came from the same value of t. And then from the next value of t, we get this y value and this x value, giving us this point. And then another point, and another point. Okay, so our graph will end up looking something like this. Now, there are other graphs that we can use, but what we can see is that if x is concave down, that's going to cause these points to become closer and closer together. Y being linear is going to cause these y values to be equally spaced. So if the x values get closer and closer together while the y values are equally spaced, that means the run between each succeeding pair of points is less than the one before it. The rise is the same, so that the slope is going to be bigger. A lesser run with the same rise is going to give us a larger slope. Now, if, for example, this is the graph of, let's say, x equals the square root of t minus 3, which would have a graph of this shape. And you should know the graphs of your basic functions, you know, the power functions, which would include the square root function or the squaring or the cubing function, t raised to any power, and then translated 3 units to the right by subtracting 3. And of course, you need to understand translations and so forth, shifts, stretches, reflections, all the graphing techniques that you learn in pre-calculus and use in a calculus course. If you're not really conversant with those at this point, you really should be, so you really need to review it. And maybe we have y equals 3t. Why not? Because I haven't written any scale on any of these graphs. Okay, so maybe this is y equals 3t. Maybe that's x equals square root of t minus 3. The x graph is concave down. The y graph is linear, and we've just seen why that gives us a graph that's concave up. Now we'll look at a couple more in another video.